Hi, folks. This is Heath. We are starting day 7 here today. We're looking at Shannon's theory, and we'll talk about that in just a second. Before we get started, I want to go ahead and make an announcement about the first exam. Just to give you a heads up, today is February 3rd. The first exam is in 10 days from now. That's going to be February 13th. That's over a weekend. But that will give people time. I'm hoping that people will have time then to do this. The exam will be open during a window of time, a 12-hour window. I'm thinking probably about 9 in the morning to 9 at night. Once you log in to the test, you'll have a 2-hour window to complete the test. And then you'll have to submit it within 2 hours after you've started it. So you'll have time to work on the test, but you can schedule it for whatever time works with your schedule that day. I'll tell you a little bit more when we come up closer to that date. I'm also going to work up a practice test to post so that people can start working through that as well. All right, so let's get started. When we talk about Shannon's theory, Shannon was Claude Shannon, who was an engineer with Bell Labs during the 1940s. And at the time, 1940s, computer science wasn't considered a field yet because computers themselves were kind of brand new. That you had engineers and you had engineers who worked on computers, but there wasn't a whole discipline. You couldn't major in computer science or get a degree in that because there just weren't enough computers out there to have a demand for computer scientists. But Claude Shannon was probably the first, at least the first American who really sort of took the idea of understanding what was going on seriously enough to study it in an academic setting. This Bell is the same as like the Bell telephone companies from the actually even going on today in some parts of the country. I was going to say part 80s and 90s before the breakup, but he worked for the company that handled the communications relays for the Bell telephone system and knew that as the World War II was brewing, that keeping that they would be communicating messages over the telephone system that had to be kept secure. And he was looking into the idea of how do you transmit messages over telephone lines in a way that keeps them secure. And he published 2 papers. And we're going to look at both of them over the course of the semester. One of them is posted to the website today. It's a little dense. It's not the easiest to read, but there's a lot of important ideas in here. I'm going to try to summarize the important stuff from the first paper. He defined 3 terms, what it means to be computationally secure, provably secure, and unconditionally secure. And what these terms mean and how we can apply these terms to different types of crypto system. So we say that a crypto system is computationally secure if we know how to break it, but breaking it requires such a large number of computations that we can expect that nobody's going to take the time to break it. So for some crypto systems, we don't know the best algorithm for breaking them. And so we might talk about the computational security of a particular algorithm of attack. So as an example, we know that the Vigenère cipher is more computationally secure than the Schiff cipher. That against brute force attack. The Schiff cipher, we know can be brute force attacked in 26 guesses, and the Vigenère cipher takes much, much more than 26 guesses to be able to break it. we have crypto systems where we know that there's a vulnerability, but the vulnerability still requires an average of, say, like the order of like 10 raised to the 30 power guesses to be able to even with the vulnerability, it just reduces the number of guesses down from like 10 to the 35 down to 10 to the 30, and 10 to the 30 is still such a large number that even with this vulnerability in the crypto system, we're going to allow messages to be sent using it anyway. That's sort of the idea. We have an algorithm for breaking it, but it is so impractical to apply that we don't have to worry for the present time about that algorithm. But as computer speeds increase and we get more and more processing power, at some point in time, this may become a concern. Moore's law says that computing power doubles every 7 years or so. And so just because it's computationally secure now, it may not be so in the future. So computationally secure is sort of a temporal setting that says, we know there's a problem with this crypto system. The state of the art right now for computing says that nobody can really take advantage of that vulnerability. So that's what computational security is. Provably secure is we have a mathematical proof that you cannot come up with a better algorithm than this for breaking the algorithm. That is, not only is it that the best known algorithm is secure, we can actually prove that algorithm is the best. That we can prove that the security is released to solving some specific problem. So, as an example, the RSA crypto system. This is a public key crypto system, an asymmetric crypto system that you'll learn about in 4176 if you take that course. That its security depends on the ability to factor a very large number. So large here is roughly about 10 to the 250 power. That it can't be, that if we could factor that number into primes, then we could break the crypto system. But we know that that's the barrier, that we can prove that it can't be solved any faster than being able to break down a 250-digit number into primes. Okay, that's the idea. We can prove that RSA can be broken if and only if the public key can be factored. And so it's computationally secure if we choose a large enough key, and we can prove that that's never going to change because that is the barrier to being able to break into this. Now, provable security still allows for other kinds of hacking, social hacking, and other ways of discovering the password. That if somebody has it written down somewhere and you know where they've written it down, then you don't have to do any of the mathematics. There are other kinds of security problems. But provable security says that we know what the barrier is to being able to break this algorithm is. And we know how long that is going to be. And nobody is going to come up later on with a sneaky algorithm that breaks it faster. So a message encoded with RA crypto system is not guaranteed to be secure forever, because computing power can increase, and so does our ability to factor large integers. And so a message that's secure today can be broken in a few years' time, but hopefully by then the reason for encoding the message won't be relevant. And then finally we get to unconditionally secure. A crypto system is unconditionally secure if it can be shown to be unbreakable even with an infinite amount of computing resources. There are some unconditionally secure crypto systems, but all of the unconditionally secure crypto systems we've ever discovered are very difficult to implement in practice. We'll talk about one in a moment that is hypothetically possible. and we'll talk about why you can't implement this in practice. So unconditional security is the goal, but so far we've never found a usable crypto system that is unconditionally secure. So this is a crypto system called the OneTime Pad. It's an example of an unconditionally secure crypto system that would work in theory. It's a variation of the LFSR that we saw last class, the machine that generates an infinite number of bits, but it generates these bits randomly, but Bob and Alice have access to the same infinite random sequence of bits. So that even though the bits are being generated randomly, Alice can generate a sequence of bits with the machine now for encrypting a message, and then Bob can later on generate that exact same sequence of bits with his machine to decode the message. That would be the idea. Because the bits are completely random, the crypto system is secure because every bit has an equal chance of being a 0 or a 1. And the way that XOR works, that every digit of the ciphertext has an equal chance of being a 0 or a 1. And so any message of the same length can't be distinguished from any message from any other one. If I have two messages and encode them both, in both messages, the ciphertext has an equal chance at every single bit of being the same. And so we have no way of separating these two messages. That's the idea for why this crypto system is unconditionally secure. The problem is that we don't have a way of generating a truly random sequence of digits asynchronously in two different machines, where Alice generates them when she's encoding a message, and then later Bob generates them. If they were random, Bob's bits wouldn't depend on what bits Alice's were generated from. That is the idea of being able to generate two identical but random sets of bits. Doesn't make sense that the second machine, if it's generating something that's identical to the first machine, it's not generating them randomly. And so that's the problem. The OneTime Pad doesn't work in practice. The way that Alice's and Bob's machines work are fundamentally different. But if we could do this, then this would work. All right. So all of these definitions involve making some calculations involving probabilities. What is the likelihood that a crypto system is going to be broken? And so for the rest of the time, we're going to talk about a little bit of business here involving random variables and the values for those. So when we talk about a discrete random variable, and the notation that the book uses is like a sort of confusing, is that they use a bold X for the name of the variable, and they use an italic X for the domain of that variable. It's a set of possible values and a probability distribution defined on X. So, for example, the easiest random variable that most people know is your standard six-sided dice. So if we have, this dice, when I roll the dice, I am generating a random variable. This is my bold X. The set of values that it takes on are 1 through 6. But associated with each number in the domain is also a probability. Consists of a finite set and a probability distribution defined on X, Well, for a fair dice, each of these probabilities was 1/6. That's sort of the idea. So that the italic X describes the entire set of possible outcomes. Bold X is an undetermined outcome at this stage so far. That's the idea. It's the variable object itself. Okay, so we require that the probability for every individual value has to be between 0 and 1, and that the sum of those probabilities has to add up to 1. So these are two things that we usually associate with probabilities, that they can't go less than 0 or higher than 1, and then the total of all the probabilities has to add up to 100%. Okay? All right. So the OneTime Pad can be simulated with a random variable, where the output variables are the random variable are 0 and 1, and the probability of a 0 is 0.5, and the probability of a 1 is 0.5. Standard six-sided dice is a random variable whose underlying set contains the values 1 through 6, and the probability for each of these values is 1 over 6. So these are two examples of random variables. All right. When we talk about joint probability, if we have two different random variables, the joint probability, the probability of a little x comma little y, is the probability that capital X is x and capital Y is y. And we say that two random variables are independent if we can do this just by multiplying the probabilities together for all x and all y. Okay? This is not always true for random variables. It's true for some, but it's not true for others. We'll see a couple of examples, I think, in a moment. So here's an example. We flip a coin and we roll a die. These are independent variables. Whatever happens on the coin and whatever happens on the die don't have any impact on the other. And so any joint outcome has a probability of 1/2 times 1/6, which is 1/12. As an example, the probability that x is heads and y is a 4 is just the probability of x being heads times the probability that y is a 4, 1/2 times 1/6. And since we can find the joint probability, the and probability, by multiplying, that's what it means to be independent. So random variables x and y are independent if the probability that x is equal to some variable x and y is equal to some variable y is equal to the probability that x is equal to x times the probability that y equals y. And in the case where x is a coin and y is a die, these are independent values. So here's an example of random variables that aren't independent. You can find the current Virginia Tech football roster at this URL. And what we're going to do is we're going to randomly select a player off of the roster. So we want to calculate the random variable that the randomly selected player is more than 71 inches tall. Well, the probability that x is a yes for that variable is 0.0807. And then y is a random variable that we select a randomly selected player and he weighs more than 200 pounds. So x is the height of a player and y is the weight of the player. And the probability that y is equal to yes is 0.0714. But the probability that that a randomly selected player is more than 71 inches tall and weighs more than 200 pounds is 0.0647, which is a little bit bigger then the product, 0.807 times 0.714. I would underline that. This is the actual probability of being more than 71 inches tall and more than 200 pounds. But this is what the product would tell us. And so it is a little bit more likely that a tall player also is a heavy player than if these were just completely independent of each other. The height and the weight of a player are not independent. And so these are random variables that aren't independent. All right. So let's look at the other definition. We've talked about joint probability. Conditional probability, which is indicated with a little vertical line symbol here, represents the probability that x is equal to x, given the fact that we have already established that y is equal to y. Okay? And we have a formula. This is true for all pairs of discrete random variables. That the probability of x comma y, this is the joint probability, is equal to the conditional probability times the probability of y, whatever y is. This, even if they're not independent. Okay. So in order for x and y to both be true, that probability, y has to be true. And now that we have established that y has to be true, then we're just looking at the probability that x is also true, given the fact that y has been established to be true. We can actually switch these around. This is also the same thing as the probability of y given x times the probability of x. So we can switch the x and the y on the right-hand side. We start by establishing that x is true, and then we then go through and establish that given that x is true, that y is also true. That's sort of the idea here. All right. So let's look at an example here involving a pair of dice. Let's say we throw a red dice and a green die together as a pair. So I've got these two dice, I throw them together. X represents the total on the two dice, and Y represents the value just on the green die by itself. Okay? So the probability that the total is 10 is 3 out of 36. There are 36 possibilities for the red dice and green dice. This is your combinatorics coming back to bite here. 6 possibilities for red dice, 6 possibilities for the green dice. So you've got 36 possibilities. To get a 10, you could have the green dice could be a 4 and the red dice could be a 6. The green dice could be a 5. The red dice could be a 5. The green dice could be a 6. The red dice could be a 4. So 3 out of 36 possibilities, which is 12. But the probability of x being a 10, given that the green dice is a 5, not the red dice, the green dice. So if I know that the green dice is a 5, then there are still 6 possibilities for the red dice, and this is the only one that will make a total of 10. And so there's a 1 out of 6 possibility that, given the fact that the green dice is a 5, that the total is going to be 10. There are 6 different possibilities because the red dice can be anything, and only 1 out of those 6 possibilities will result in a 10. And so if I know that the green dice is a 5, the odds of having a total be 10 went up. But if I know that the green dice is a 2, then the probability of having 10 as a total goes down, because If the green dice is a 2, it doesn't matter what's on the red dice. I can't make a total of 10 anymore. And so the probability is now 0. So that's how these conditional probabilities work. Without any information at all, I have a 1 out of 12 chance of rolling a 10. But if somebody tells me what the green dice is, knowing that the green dice is a 5 raises the chance that my total is going to be 10. And knowing that the green dice is a 2 lowers the chances that my total is going to be 10. Okay? All right. So we have one last theorem here. For all pairs of discrete variables, the joint probability of x given y is equal to the not joint probability, the condition probability of x given y relates to the joint conditional probability of y given x by this fraction here. We could have rewritten this as the probability of x given y is equal to the probability of y given x times a conversion factor that switches the order of the conditional cases. And to switch that order, the conversion factor is the probability of x over the probability of y. Now, the proof of this theorem is not hard, and the proof comes way back to, I'm going to back up 2 slides. Right here, this definition here. That this is x and y, and I mentioned that since x and y is the same as y and x, the order of x and y doesn't make any difference, these two things were the same. And that's going to be the first step in the proof. The proof is that the probability of x and y, not and y, sorry, is equal to the probability of y and x. And therefore, the probability of x given y times the probability of y is equal to the probability of y given x times the probability of x. And now for the third step, I'm going to just multiply both sides by 1 over the probability of y. So 1 over the probability of y times the probability of x given y times the probability of y is equal to the probability of y given x times the probability of x times 1 over the probability of y. So this is the definition from the 2 slides ago. This step we just multiplied by 1 over the probability of x, probability of y, sorry. And on this side they cancel, and on this side this is exactly what we want. Probability of x given y is equal to the probability of y given x times the probability of x over the probability of y. Ta-da! Or as more formal mathematicians like to write QED, but that finishes up the idea here. So Bayes' theorem is not a hard theorem. It allows us to switch the order of a conditional probability. If the part that we were expecting to happen first ends up happening second, we can make an adjustment. This is just the adjustment factor that we have to make. Okay? All right, no class on Friday. When we get back on Monday, we're going to look at a couple of examples of using Bayes' theorem and talk a little bit more about Shannon's paper. And then we'll try to spend the rest of the week getting ready for the test and doing some practice. All right? Thanks for coming. I'll see you guys Monday. Have a good long weekend.